great pleasure to introduce to you Alexey Elagin from Sheffield. He's going to speak to us about atomic semi-orthogonal decompositions or derived categories of surface. Please, Alexey.
Okay, thank you very much for the invitation. It's my great pleasure to be here and to tell something about atoms to people who also do atoms. I should make a disclaimer that atoms that appear in my talk are quite, or maybe not quite, but are essentially different from the atoms that we've seen before that. They have the same name because they probably have the same nature, but as they appear quite differently, as you will see. So atoms that you'll see in this talk are pieces in the derived categories of algebraic varieties, but they will and may play the same role to help understand birational isomorphisms and abstractions to birational isomorphisms between varieties. And this is based on our joint work with Schneider and Evgeny Shinder. So the plan for the talk is to answer three questions. Why, what, and how. Why we should care about derived categories, semi-orthogonal decompositions of the derived categories, and in particular atomic decompositions. What we call an atomic theory, and what we have proved. This will be a very short part. And finally, how we construct atomic theory for surfaces. Maybe I won't tell today how we use this theory, but if you go to Rio, you'll hear how we apply theory to some problems of birational geometry. So I would like to start from the first part, motivating. Maybe that's the major part of my talk. And not everyone is an expert in derived categories. I probably would like to stop for a while on this slide and to help you feel more confident about derived categories. So to any algebraic variety, and for us algebraic varieties will always be smooth and projective. And for a while let us assume that the base field is algebraically closed. To any such variety, one associates a category called the derived category of the variety. dx. The objects of this category are bounded complexes of coherent sheets. And morphisms in this category are not easy to describe, but the idea is that you start from taking just morphisms between complexes that commute with the differentials, and then you formally invert some family of morphisms that are called quasi-isomorphisms. And the idea behind this formal inversion is that we identify, for example, any sheet and all its resolutions. Identify all complexes that are quasi-isomorphic. We get a category so the category of coherent sheaves is abelian, and the derived category of coherent sheaves is not abelian anymore. It has a nice structure called triangulated category. So the structure is characterized by two pieces of data, by an autoequivalence of this category called shift functor, which takes a complex and shifts the gradient. And with a class of distinguished triangles. So a triangle in this category is a diagram of this form, where A, B, and C are complexes. So some class of such diagrams is chosen and called distinguished triangles. This data should satisfy some axioms, and essentially main axioms say that any morphism F fits into some distinguished triangle. Then the third vertex is called the cone of F. It is uniquely determined by F. And then also there is an axiom saying that triangles are in fact triangular, so that three vertices play the same role. There is no first, middle, and last term. They all are equal, and if you rotate a triangle, you also get a triangle. And these triangles replace what we have for abelian categories as extensions, kernels of epimorphisms, and co-kernels of monomorphisms. All these three constructions in triangulated categories are obtained just by taking a cone of some morphism. In many aspects, triangulated categories are better than abelian. So originally, derived categories were invented by Grothendieck as a smart way to do homological algebra, to make some computations of derived functors. Later it was discovered that the derived category of an abelian category as a whole is an interesting object as a whole, in particular for an algebraic variety. It can be used to study geometry of the variety. Obviously, isomorphic varieties have equivalent derived categories. The converse in general is false. However, for some varieties, they can be uniquely reconstructed from their derived category. If you have two smooth projective varieties and one of them has ample or anti-ample canonical class, then derived equivalence implies that varieties are isomorphic. So let us see how derived categories can reflect geometry of varieties. And the main tool to understand this, to do this, is called semi-orthogonal decomposition. So a semi-orthogonal decomposition is given by an ordered collection of subcategories, so that these subcategories are full and triangulated, where triangulated means that they are stable under shift functor and under taking cones of morphisms. If two vertices of a triangle belong to a triangulated subcategory, then the third vertex also belongs. And semi-orthogonal means that if I take an object in one category and an object in another subcategory, then from right to left there are no morphisms. And decomposition means that all these categories taken together generate the whole derived category. An example is given by a decomposition found by Williamson. For a projective space, there is a nice semi-orthogonal decomposition into n+1 subcategories, where subcategories are generated by consecutive line bundles OI. Actually, for any n+1 consecutive values of I, for example, from -n to 0, and any such subcategory is very small. It is the smallest possible triangulated k-linear category. It is just derived category of k-vector spaces. And this decomposition is a special case of a decomposition induced by an exceptional collection in a derived category. Maybe I'll skip this slide. We'll need exceptional collections when we construct decompositions in the third part of the talk. Most of our decompositions are generated by exceptional collections. So let me better show you the main semi-orthogonal decomposition that motivates what we will do next. So-called blow-up formula found by Orlov. It describes derived category of the blow-up at a smooth locus in terms of the derived categories of the base and of the blow-up center. As you can see, this formula is very similar to a formula that we've seen yesterday. That was for cohomology, for a blow-up. We have one copy of the derived category of the base, and could I mention -1 copies of the derived category of the blow-up locus. Blow-up center. And there is an even more general theorem by Bondel and Orlov that derived categories for varieties connected by an elementary birational transformation such as standard flop and standard flip. A standard flip takes a subvariety which is isomorphic to some projective space Pk, blows it up and replaces it with another projective subvariety of possibly different dimension. Let me assume that it replaces Pk with Pl, where k is greater than L. And if k equals to L, then this is called a flop. Such transformation, the composition of the blow up and the blow down is in general just a birational and not biregular. But it was discovered that for a flip, the derived category of the smaller variety is embedded as a component into some semi-orthogonal decomposition of X. And if this is a flop, then the categories are equivalent.
Sorry, what do you mean by smaller?
We'll see it on the next slide. Nothing precise at the moment, but I'll explain what this means precisely very soon. We've seen Mukai flops yesterday, and in particular, in small dimension, Mukai flops also produce derived equivalences between two parts of the flop. So, looking at this, it's very natural to understand that probably all minimal model program can be translated onto the language of derived categories and semi-orthogonal decompositions. So, minimal model program takes an algebraic variety and looks for a minimal model by contracting something that can be contracted, that is not necessary, and then possibly terminating at some minimal model. So, the idea behind minimal model program is that we try to reduce the canonical divisor. If it is positive on something, we want to contract this something and make canonical class smaller. So that's the idea behind minimal model program, and possibly the same could work for derived categories. We can replace varieties by reducing their canonical class and at the same time reducing their derived category by replacing it with some semi-orthogonal component. So now let me explain what we can mean by saying that one variety is smaller than the other. We can compare the canonical classes. Assume we have a birational isomorphism. Then it is called a it's called a k-equivalence if canonical classes on both sides can be compared. To do this, you need to construct a common resolution of such a birational isomorphism by finding a dominating birational variety so that these are birational morphisms. This is smooth. Then you can pull back canonical classes from X and Y to Z and compare on Z. If we have an equality, this is a k-equivalence. If we have an inequality, so that the difference is effective, then we have a k-inequality. And it was conjectured by Kawamata that k-equivalence implies derived equivalence and k-inequality implies that one derived category sits in the other as a semi-orthogonal component. In some cases, this conjecture is proved. In dimension 2, it's more or less trivial. In dimension 3, it essentially follows by birational results for equivalence. But in general, it's wide open. And here is another motivating conjecture that we also have seen in maybe under some different angles. It relates rationality of a cubic fourfold and properties of a certain semi-orthogonal component in its derived category, known as Kuznetsov's component and denoted here by AX. So for such cubic hypersurface, you can consider an exceptional collection of 3 line bundles restricted from the ambient projective space. They form a collection which is not full, so you can complete this into a semi-orthogonal decomposition by adding some subcategory A. It has 2 Calabi-Yau property, meaning that the Serre-functor is isomorphic to the shift by 2. And it is conjectured that X is rational if and only if this subcategory is equivalent to the derived category of some K3 surface. As you can see, it's quite similar to Hassel's conjecture for cubic fourfolds and cohomology that we've seen yesterday. Primitive part of the cohomology corresponds to this primitive part of the derived category because we remove, roughly speaking, we remove what is restricted from the ambient projective space by considering this complement. Now let us see how we could approach such problems, and let us have a look once again at the blow-up formula. What we see is that for a blow-up, which is an elementary birational transformation, derived categories are obtained one from the other by adding some pieces that come from small dimension. And any birational isomorphism is decomposed into a chain of blow-ups and blow-downs. Therefore, we can say that derived category of X and Y are related. We need to remove and to add, and then to remove and to add some derived categories of varieties having dimension not greater than dimension of X minus 2, because this is the dimension that we can blow up. So it's natural to ask what remains unchanged when we do such operations. We change a little bit these derived categories, but what remains unchanged? Can we discover birational invariants inside derived categories? How this could work? Let us go back maybe 20 or 30 years in time and imagine how we could make this work. Let us just take a derived category and decompose it semi-orthogonally as far as you can. If your component can be further decomposed, you decompose it. Then you stop when you cannot decompose any of your pieces anymore. Let us call this maximal decomposition. And let us say that components of any such maximal decomposition are categorical atoms of a variety. Atoms means indecomposable in Greek, so this is very natural to do this. Now let us see which atoms can be added or removed when we make a blow-up. These are atoms that appear as atoms in derived categories of varieties of small dimension. That is dimension of X minus 2. Let us call these atoms trivial, and the atoms that don't appear in these derived categories non-trivial. So by the blow-up formula, non-trivial atoms are birational invariants. We can use these invariants. We could use these invariants. For example, if this program could be realized, then automatically we would obtain decay equivalence conjecture for varieties or general type or varieties with globally generated canonical classes. If your X has globally generated canonical class, then its derived category has no semi-orthogonal decompositions. It is simply indecomposable, so it has to be its own atom, the only big atom, all dBx. So then this atom is not trivial. If X and Y are birational, then the atoms should be the same, so they should be, these two varieties should be derived equivalent. And also Kuznetsov's conjecture in one direction: if rational, then the component is equivalent to dB of a K3 surface, also would follow quite easily. But unfortunately, this approach does not work. Because we say of a maximal SOD, but they can be different maximal SODs, and they may have different atoms. So atoms are not well defined in this way. And actually this was understood quite long ago. The most elementary and classical example by Bondel shows that there is a finite dimensional algebra, so that the module category, the derived module category, has an exceptional collection of 3 objects, and also it has another exceptional object, so that the orthogonal component has no exceptional objects, and it produces 2 essentially different indecomposable atomic decompositions. A more recent and more striking example that I would like to show you, because it also happens on a surface, was found by Krach. Let us take a general blow-up of P2 at 10 points. That's a rational surface. And you can construct 2 exceptional collections of line bundles on this surface, having the same maximal length, 13. One collection is full, so it gives a semi-orthogonal decomposition. And another collection is not full, so there is some extra component, denoted here by P, that completes a semi-orthogonal decomposition. And it shows that atoms are not well defined, because on the left we have one collection of atoms, and on the right something quite different. Therefore, this naive approach outlined here does not work. What can possibly work, and that was advertised by Kontsevich, is that decompositions should be taken not as something natural, but as some extra data that we choose. So we decide that we choose a class of good semi-orthogonal decompositions that we plan to use, and we ignore all other decompositions because they are not the right ones. So we should choose a class of good semi-orthogonal decomposition for any variety, and then we can try to do something with this. It looks like we have managed to realize this idea for surfaces. Most of the talks about atoms here deal with at least 4 folds and aim at rationality or irrationality of 4 folds. On contrast, we go one step back from 3 folds, we go to surfaces. It doesn't have so far many interesting applications, but it still has some. And also existence of such natural decompositions is interesting by just in its own. I think that everything that we've done could have been done 20, maybe more years ago, so there is nothing new that we use. But somehow it wasn't done. So what do we do? From now on we restrict onto surfaces, and let us, oh no, sorry, not now. This is what we want, what we would like to construct. An atomic theory. So an atomic theory consists of a class of varieties that we consider, a class of morphisms between them that we allow, and a class of good atomic semi-orthogonal decompositions. Atomic is just a word, it's not a property, that's a name for the right decomposition. Before coming here I did not realize how bad this name is, but now it's too late, we call them atomic. We fix a class of atomic decompositions for any variety of the class, and these decompositions should satisfy just 2 properties. One is the property 1 says that all atomic decompositions are mutation equivalent, and this essentially means that they are all determined by each other. I'll explain mutations in just a minute. This property says that essentially we just have one good decomposition. And the second property is the main one. It says how atoms are related under under admissible morphisms. In particular, in applications, these morphisms will be just blow-ups of surfaces. So the condition says that for any such admissible morphism, the pullback functor from derived category of y to derived category of x is fully faithful. And this condition of fully faithful means that we already have a semi-orthogonal decomposition of dby is it f? Oh, sorry, it is x to y. This condition that the derived pullback is fully faithful is equivalent to the condition that the derived push forward of the structure sheaf equals to the structure sheaf. If this is satisfied, then derived pullback is fully faithful, and automatically we have a semi-orthogonal decomposition of x into two pieces: the kernel of the push forward and the image of the pullback. This condition says that if I take there are two atomic decompositions that agree with this decomposition on the blackboard. I replace dbx with its atomic pieces. No, sorry. This was y. I replace dby with its atomic pieces. I add some extra pieces decomposing the kernel, and I get an atomic decomposition of x. So this is compatibility condition under admissible morphisms. Let me explain mutations briefly. Any any semi-orthogonal decomposition defines many more semi-orthogonal decompositions by mutations. You pick some subcategory and you can move it to the left or to the right by jumping over its neighbor component. So if I make a right mutation, I take this AI and move it one step to the right between AI plus 1 and I plus 2. There exists unique such decomposition, and it's called ith mutation of the original decomposition. Left mutations are defined similarly, and I can apply such mutations many times and get many more semi-orthogonal decompositions. These mutations together define the action of a braid group on the set of all semi-orthogonal decompositions of the same length. And an important property is that when I make a mutation, new component is equivalent to the old component. So that equivalence classes of these subcategories remain the same. And therefore, I can consider these components of any atomic decomposition up to an equivalence as atoms of the derived category. For all atomic decompositions, atoms are the same. And in fact, we have constructed such atomic decompositions not just for surfaces, but for surfaces with a fixed group action, for G surfaces. And in particular, we can apply this to the Galois group action and obtain atomic theory for surfaces over any non-closed but perfect base field. But to construct it, we work over an algebraically closed field and possibly with a group action. So we fix a group, consider G varieties, G equivariant morphisms, and this definition is not much different from this one. In particular, you can see that the conditions are exactly the same. what is important that when we consider G varieties, we consider the compositions of the dBx, just of ordinary derived category of x, and we require all our components to be G-invariant. So they are preserved by the action of a group and used from the derived category. And that's it.
Sorry, the group can be finite.
The group can be almost arbitrary, it can be infinite, it can act non-linearly, as Galois group does. There is some technical information needed to make MMP work, but essentially this is very general group action. You can have almost any group action. Now, what we have proved. So to have atomic theory, we need to fix a class of varieties and class of morphisms. So for us, class of varieties is G surfaces over fixed base field K, which is algebraically closed. And as a morphisms, we consider G equivalent birational morphisms. For any birational morphism, push forward of the structure sheaf is the structure sheaf, so there is semi-orthogonal decomposition as on the blackboard, and we can require property from the definition of an atomic theory. So first result is that G-atomic theory exists for surfaces with a group action under some technical conditions that I prefer to not to discuss. And as a corollary, we get that atomic theories exist for surfaces over any perfect non-closed base field. Surfaces here are smooth and projected. Now, how we prove this? This is here the third part of the talk starts. Our construction is based on birational geometry and minimal model program for surfaces. In contrast with Hodge atoms that are defined in some natural way by some uniform construction, we introduce atomic decompositions ad hoc. So we consider some cases, we introduce decompositions by some explicit formulas, and then we check that everything works well. But there is no natural way to extract these formulas from somewhere. We just write them and see that it works. I should make a very brief reminder of the minimal model program for surfaces, which is not a rocket science. The basic operation is blow up. So for G surfaces, the basic operation is blow up of a finite G orbit. It replaces a finite orbit by a finite collection of disjoint -1 curves, which belong to the same G orbit of curves. And the inverse operation is the blow down, G equivalent blow down, if we have a disjoint collection of -1 curves that belong to one G orbit. We can contract them simultaneously and get a smooth G surface. Any birational, G birational isomorphism is decomposed into blow-ups and blow-downs of such orbits. And if you have a surface which cannot be equivalently contracted, it is called G-minimal. So how we construct a minimal model for a given surface? We contract G equivalently as far as we can, and then we terminate at a G-minimal surface. And such a G-minimal surface can be of one of three types. It can be a surface with numerically effective canonical divisor, or it can have a structure of it can be a Delpezza surface with G-Picard rank 1, or it can have a structure of a G-conic bundle over some smooth curve.
The action need not to be linear, these two.
Not necessarily. If we have no group action, then the only possible output in case 2 is just P2, projective plane. And in type 3 we have ruled surfaces over some curves. So that these are P1 bundles where all conics are P1s, are irreducible. In general, when we have a group, conic bundles may have reducible fibers. So a conic bundle in G-invariant setting may look like this. And this is relatively minimal if the group permutes two components of a reducible fiber for any reducible fiber. Then you cannot equivalently contract it over the curve. So there are three possible outputs, and outputs number 2 and 3 are called modifiable spaces. So there is a structure map from X to a point in case 2. That's a modifiable space over a point. And there is a structure map to a curve. Case 3 is called modifiable space over a curve. And this chain of blowdowns in general is not unique. So we may have different minimal models starting from our surface Y. But a good point is that in case 1, this minimum model is unique and the chain of contractions also is unique. So from birational geometry perspective, case 1 is not interesting, while cases 2 and 3 are more interesting and have richer birational geometry and more semi-orthogonal decompositions. So that's the plan of the proof of our theorem. We follow minimal model program and define atomic decompositions following this chain of blow-ups. We take so for one blow-up, let me show you the property in the definition. If F is a blow-up, then we need to take atoms of the target, pull it back to X, and then add some extra components, splitting the kernel of the push-forward functor into some atoms. So it suffices to explain how we split this kernel and also what are the atoms of the target. And this is done on step 1. Then it remains to introduce atomic decompositions for their minimal surfaces. That's step 2. After that we have defined some atomic decomposition for any G surface. But it depends on many choices that we make when running MMP. So we need to check that up to mutations, these decompositions don't depend on the choices that we make. And that's the main thing where you have to prove something. After you have proved that definitions are good and compatible, we just need to check that these decompositions satisfy axioms of an atomic theory. So for axiom 1, actually there is nothing to check, because what we do, we introduce just one decomposition, say this decomposition is atomic, and then all other atomic decompositions arise as its mutations. So property 1 is fulfilled just by design, and for property 2, we'll need to say something. Now, let's do these steps. Here is step 1. When I blow up an orbit, there is a decomposition coming from Orlov's. Essentially, this is Orlov's blow-up formula. Here are atoms that come from Y, and the kernel of the push-forward functor, in this case, is generated by an exceptional block of torsion sheaves concentrated on the -1 curves. Maybe I should go back and show you the slide with exceptional objects and collections. Yeah, so an object is exceptional if it has as little self-endomorphisms as possible. There are no higher x's, and the endomorphism algebra is just one-dimensional, it's K. A collection of objects is exceptional if there are no homes from right to left, and null objects are exceptional. Finally, an exceptional collection is full if these objects generate all the derived category. Here is an example of an exceptional collection, line bundles on Pn from minus n up to 0. An exceptional collection generates a semi-orthogonal decomposition. And also we'll need to understand that exceptional objects may be organized into blocks. If I have some exceptional collection where all objects are pairwise orthogonal, not just semi-orthogonal but completely orthogonal, it is called a block. And we write such collections or pieces of a larger collection vertically and call this a block. So, for a blow-up of a surface, by Orlov's formula we add derived categories of the blow-up center, which is a finite collection of points. So to any such point we add one exceptional object, because structure sheaf of a point is exceptional. And these structure sheaves of a point correspond to twisted structure sheaves of -1 curves. And these curves belong to one G orbit. So this subcategory on the left is G-invariant, and also it's G-indecomposable. So we actually don't have any choice, we just have to take this block of torsion sheaves and add it as a new atom for one blow-up. Now we need to understand what are atomic decompositions for the minimal surfaces. And there are three types of minimal surfaces. Surfaces with kx and f, modifiable spaces over a point, which under a group action can be delta surfaces of almost any degree. They are not minimalist surfaces, but when a group permutes -1 curve sufficiently well, they become G-minimal. And finally, modifiable space over a curve is also characterized by its degree, which is essentially the same as the number of reduced fibers. Yeah, to be more accurate, here the curve is P1. These degrees appear only for modifiable, for conic bundles over P1. Over rational curves, it's a different story. And for any surface for any modifiable space of these types, we'll demonstrate some explicit semi-orthogonal decomposition. Let's go. For surfaces with kx and f, we just take one big atom. The whole derived category becomes an atom. For a conic bundle over an irrational curve, we have two atoms. We can consider a morphism to the base as on the blackboard. It satisfies the push-forward condition, so we have a decomposition as on the blackboard, and we take these two pieces as atomic pieces of X. Then, for conic bundles which are rational and for Delphi surfaces, we distinguish two cases, large degree and small degree. And somehow they behave quite differently. For degree small, we have just two atoms, the structure sheaf and its orthogonal complement. And similarly for a G-conic bundle of small degree, we take the decomposition on the blackboard that comes from atomic decomposition of the base of P1. There are two structure sheets, two line bundles, and the kernel as the third atomic piece. And the most complicated case is surfaces that have large degrees.
So here I need some notation. For a rational surface, we can consider birational contractions 2p2, and we denote the divisor classes that define these contractions by letters H capital. There are finitely many such contractions. And also there are conic bundle structures that are given by some divisors, and we denote these divisor classes by H small. There are finitely many of such. For example, if you have a Delpezzi surface of degree 6, which is the blow-up of P2 at 3 points, such surface has two birational contractions to P2. One if I blow up, I can blow up down what I have just blown up, or I can do Cremona transformation and blow up to 3 different -1 curves. So such X has a cycle of 6 -1 curves. I can pick up 3 disjoint and contract them and get 2 birational contractions to P2. They are given by 2 classes H capital 1, H capital 2. And there are 3 conic bundle structures on such X. Essentially they correspond to projections from 3 points on the plane that I have blown up. They become regular on X and they give 3 conic bundle structures. So these are H small 1, 2, 3. Having this notation, I can introduce atomic decompositions for 4 possible cases. P2, P1 times P1, and Delpezzi surfaces of degrees 6 and 5. Here they are. On P1 times P1, I have 2 classes H small, which are 2 fibrations. And on X5, I have 5 fibrations over P1, and I also have extra component generated by E. E is certain exceptional rank 2 vector bundle.
It doesn't depend on the group G.
It doesn't. For such surfaces to be G minimal depends on the group G. So the condition is that for the group action, this is G minimal. And if it is, the compositions don't depend on the group. As you can see, these H capital and H small classes are defined invariantly, so they are preserved by any automorphism of the surface, they are preserved by group action, and these components are G-invariant. In any case, we have 3 components, 3 atoms.
But isn't this just a consequence from the fact that you went to the G-equivalent minimum model problem, or really in these SLDs are more or less specified by what should come from them?
In fact, in most cases it is. So it looks like I take something from out of nowhere, but in fact there is no big choice that I have. Almost all of these naturally follow, of these formulas naturally follow from our properties, and also some other properties that I removed from the definition, but there are a little bit more morphisms that we allow, and they give more constraints and help to understand that these are the right decompositions. Finally, if I have a conic bundle of large degree over P1, any such conic bundle is either a Hirzebruch surface, where I just take a full and exceptional collection of line bundles, or it is Delpezzi surface of degree 5 or 6, and in this case I take this decomposition. One of these H small classes defines structure map of a modifiable space, so it is preserved by the group action, and I split it as a separate atom. For example, I can denote it by H3 or H5 respectively, and move aside. If group action preserves modifiable space structure, then this extra line bundle is invariant, and I get 4 atoms. Now on step 3, I have to prove that our decompositions don't depend on the choices of MLP. I I'll very briefly go over this part. Essentially, we use Sarkisov decomposition of birational isomorphisms. It says that any G birational isomorphism between modifiable spaces decomposes into elementary ones, and it can be shown that it suffices to check compatibility only for the Sarkisov links for some elementary birational transformations. They are given by one of these diagrams. They are all classified in the sense that we know what are degrees of the surfaces that are involved in these diagrams. Yeah, this is a classification of links, and maybe I'll show how it works on one of the elementary examples of a link, what we actually need to do. So we start from P2, blow up. This is the example that I'm thinking about. Yes, I blow up 2 points on P2, get a surface with 3 minus 1 curves organized into a chain. These are 2 exceptional divisors, and this is an extra minus 1 curve. And I can contract this extra curve and go to P1 times P1. This is a modifiable space over a point. This is a modifiable space over P1. The composition is a link, a birational transformation. So for this P2 I have an atomic decomposition. For this modifiable space I have an atomic decomposition shown on the slides in green. Then I can pull back a decomposition from P2 on Z and pull back decomposition on this to Z. Then I get 2 different atomic decompositions on Z, and I have to prove that they are mutation equivalent. Here on the slide you can see a chain of mutations that transform one decomposition into another.
Where is the green that you said, Alexey?
Green. Yeah, here we have a definition for P1 times P1 over P1. This is F0. We have 4 exceptional objects. No, sorry, maybe that's not the case. We have X8. I assume that the group acts so that it permutes 2 points, because this is a G link. So this P1 times P1 that's definition for P2, 3 atoms. And that's definition give me a second. Sorry, I'm sorry. This is not the example that we need to draw here. There is no equivalent morphism to P1. I'm sorry. The group interchanges 2 points, so it interchanges 2 vibrations on this product. So this is a G minimal delta surface of degree 8. It also is a modifiable space over a point. So on top and on bottom we have 2 atomic decompositions on these minimal delta surfaces with extra component coming from a blow up. And there is a chain of mutations that transforms one into the other. And the core of the proof is that we make similar mutations in 20 plus different links coming from this classification of links. And in any case, we solve the exercise. It works. And luckily, on step 4 of the proof, when we have to check the second axiom, there is nothing to check, because the only operation that we need to check is blow up, and by definition of the step 1, our decompositions are compatible for a blow up, just by construction. So that's it. Thank you.
Questions?
So this Sarkisov link, you have many dimensions, and you can always, I don't know, if you blow up differently two things, then you can always spin them. If I understood correctly.
In high dimensions, this is only a program, so it is more or less proved in dimension 3, but in high dimension, that's only... It is supposed to work, there is a definition of links, but the fact that any birational transformations can be decomposed into links is not true.
Other questions?
All of this is over any algebraical suite.
Yes. And by Galois descent, we can make this work over any perfect field.
Other questions?
So what are, in the end, what are the morphisms in this atomic theory? So these G-invariant blow-ups will be the morphisms that we consider, and also the somehow there was, as a part of the definition, you had a collection of morphisms.
Mm-hmm. So in the theorem that I have shown you on the slides, morphisms are G birational morphisms. And then such morphism is a composition of G blow-ups. But actually, what we really prove is a little bit stronger. We consider also structure morphisms of modifiable spaces as admissible morphisms that are not birational because they go to smaller dimension. But they also satisfy this property, and our decompositions are also compatible with such structural maps of conic bundles.
Other question? Maybe I have one question. So, in your definition of atomic theory, I was expecting that you would, I guess, separate the special role into the possible appearance of Kuznetsov components somehow. I mean, so no design for that.
How could we
I don't know.
let it play a role?
I mean, because for instance, you think about the case of scheme for folds and Bushomukai, respect these rationality questions related to that precisely component. I mean, does the theory like if you're going to propose this, shouldn't count with the possibility of other fields?
I think that this component is actually decomposable.
Yeah.
So
This
it is clear that there is nothing. Atomic decomposition can be nothing else than this decomposition that appears in the conjecture, just because of natural properties. But you're right that we have very minimal collection of axioms, essentially just one axiom in the definition. And if you want to do this for high dimension, you may want to add more natural conditions that atoms should satisfy. But we did not do this because we only can make it work for surfaces. So maybe that is to be done if someone can make it work further to understand these extra conditions.
So let us take Alexey once more. Next slide is introduced to you Adriana da Silva from Universidade de Tarapacá, Chile. She's going to speak to us about Maxwell strata and the sub-Riemannian problem, unsolvable, non-important, regular 3D groups.
Thanks, Andrea. Okay, I would like to thank the organizers Professor Odin in particular. It's always a pleasure being here in Campinas. Like I live like most of my academic life here in Campinas, so it's always a pleasure being here. And I have to start by warning you, as I told you there, that I'm really close to the part of the end of related topics, because it's really far away of what you guys have been talking the whole week. I swear that all the talks that I could watch, I try to find some relation, but it's really far away. But hopefully that will change in the close future, okay? And why I'm saying that is because I myself also am not a geometer. I work in control theory, okay? And so you guys are asking, what am I doing here, okay? So that's actually I starting work with Professor Lima, or Professor Germa, and a PhD student of mine, and also another professor here from the department that works on dynamical systems, okay? So the idea basically it was try to find a link between us. I worked here, and when I was here, I couldn't work with the professor for here. I had to leave just to actually find something to work. So that's something that we started. And the basic idea is try to look at Subramanian geometry. Okay, so what's Subramanian geometry? That's basically it's a geometry that we have a metric that's also given by infinite curves. Basically that. Okay, this appears from, for instance, in Carnot-Theodori distance. This kind of geometry, some physical examples where you have somehow constraints on your systems, okay? And this more contemporary approach with the name of Subramanian geometry is not so old, it's from the 80s, I think. And starting the works of Gromov. So basically for us here, a Subramanian structure on a manifold will be a distribution of constant rank, okay? But we ask what people usually don't do. We ask that this distribution to be totally non-holonomic or Bragg generating, in the sense that we don't want to integrate. On the contrary, we want to somehow connect this, like the horizontal curves, with the whole topology of the manifold. Okay? So for us, the definition is much more general. We just ask for this distribution to be Bragg generating, okay? Constant rank here is because the work that we will talk here has constant rank. It's basically a contact distribution. And what we ask is that we have a smooth inner product in this distribution, meaning that you can actually calculate distance of horizontal curves. Okay, that's the basic idea. And then a horizontal or admissible curve for us will be a curve that satisfies that slip sheet, okay, and is written locally like this, okay, where this F1 up to Fk, it's a local orthonormal base of delta, the distribution that I want, okay, and U is essentially Baldwin measure. Okay, the condition in U here is basically to assure that you actually have solutions of this, because this is basically a non-autonomous system, okay, so you have solution in the sense of Katzarkov-Kontsevich-Pantev-Yu. And you can, in fact, prove that under these conditions you have actually existence of solution in small time. Okay? And here is basically where the control part enters, because here we are looking here is basically a solution of a control system with where the controls here are just essentially Baldwin measure. And then here you can look at the problem in a more dynamical way, okay? Including the concept of distance that we use here. The Subramanian distance is basically, since we can calculate length of vectors in the distribution, okay, then we can define what is the length of an admissible curve in the conditions that I defined here. And you define as being this because of the imposition that I put on the contour, that's well defined. And what you have is that the Brecht generating condition by the Reshef-Schroth theorem implies basically that their systems controllable, meaning that you can connect any two given points. Okay, that forces the metric here to be finite, and actually an extension of this Reshef-Schroth theorem shows that actually this metric is not only finite, it's continuous, and generates the same topology as you have in the manifold. Okay, so the nice part is that you have now a metric, you are in a metric space, as in the Riemannian case, and the metric is also given by infimum of curves. Okay, but the only problem here is that the curves are only the admissible one, or only the horizontal one. Okay, in fact, under this more contemporary approach, you actually have that Riemannian manifold is also sub-Riemannian manifold, where your distribution is basically the whole tangent space in this sense. Okay. Okay. Yes, Reshef shows where the controllable part appears. And the nicest part here, well, you have the problematic part is that since you don't have all the directions in tangent space, you cannot do as you do in the Riemannian case, meaning that one point in one direction defines your geodesic or your solution as you want. So here you have to go to the cotangent bundle. Okay, so think as the covector as some optimal direction that you can actually look. It forgets the direction that are. It forgets the direction. It looks only on the optimal things that you want. Okay, so when you pass the problem to your cotangent bundle, what happens is that the solutions actually only the solution that we are interested in here, the length minimizer that we call normal extremal here. Are basically the solution of this this order 2 Hamiltonian here. Okay, and that's the interesting part because you start with a control problem, and then you show that any minimal any minimizer here, meaning the solution that connects P and Q and satisfies this infimum, actually is the solution of this Hamiltonian system here. Okay, and the reciprocal is also true, meaning that at least in this normal extremal case, why I'm just talking about this because it's basically the case that we are interested in this presentation. Okay, but basically what you have is that the solutions here are in fact geodesic in the sense that these have constant curvature that's non-zero, constant length, sorry, constant speed, non-zero, and are locally length minimizers. Okay, so basically your problem is to look at this Hamiltonian, and the solution of this Hamiltonian is just project to the manifold that you are working with. Okay, so you take your problem, go to the cotangent bundle, and basically your problem is to analyze this kind of thing. Just a comment. The solution of this Hamiltonian here is what we call the normal extremal. You have also in this context of sub-Riemannian, when you are not in the Riemannian case, you have also the context of an abnormal extremal. Okay, the abnormal extremal. Right now I'm not interested in them, but they are a little bit more wild in the sense that basically this guy here, the connection between this system here, the Hamiltonian, and the length of the curve gamma is that basically this lambda fu q here is basically the contour that you get to get the Hamiltonian associated. And in the abnormal case, you have basically that all these contours, the components of the contour here have to be zero, meaning that abnormal extremos, the covector associated with the abnormal extremos, will be zero on the distribution. So the thing is much more complicated in this sense. Okay, but for our case, we are in the content case. Okay, we'll basically consider a Lie group. Okay, so I think that's one thing that's common. We work with invariant problems also. Okay, and we, as a starting point of this collaboration, the idea was to find a problem that that have not been approached. Okay, so we start obviously usually for groups of low dimension, and then we start to look at the 3D connected groups. Okay, so Heisenberg is the classical one. We have a lot of works on the Heisenberg groups, but we also find completely optimal synthesis in SO3, SO2, and SL2. And in the solvable case, we have here also a really complete study on SE2, SA2, and the Cartesian of the solvable group, two-dimensional solid group with the torus. But the non-popular Lie groups, I mean non-popular because usually you get this kind of groups because they have close connection with application. And these guys here, we did not find anything in the literature that were working at least with the idea of find a complete optimal synthesis of these guys, meaning find the expression of the geodesics, find basically what I'm interested in here is that the cut time, the time where we lose optimization and things like that, we didn't find anything, okay? And then we start to look into these groups. And soon enough we discovered why there's not many results in these groups, okay? So just a remark here, how we look at the 3D solvable, the algebras here, is basically the same direct product because it's easier, okay. It's actually, for me, it's easier to look in the same direct product way because basically you have two components. You have one dynamic in R and one dynamic in R2 that you don't need to necessarily look at components, basically the dynamics. That's the way we are interested in looking at things, okay? So with this characterization of the 3D solvable algebras, okay, basically you have the same direct product where your matrix theta is in one of these classes, okay? And the connected simple connected groups is basically the same direct product also, okay? And what happens here is that in this case, we somehow recovered, we were not looking for this result in particular, but we found a paper of sorry, here's the name. Where is the name? Sorry, here. A paper of Vershiki that basically says that we have, that calculates all the subrimany structure that we have with another name, of course. And basically they are all isometric up to, rescaling of the norm. So we can basically look at this kind of problem. The subrimany structure that we are interested in is basically a contact one because one-dimensional there's nothing to do because there's no Brecht generating. 3-dimension is Riemannian. Okay, so we have a contact one that will be basically, since we have the invariant problem, will be basically defined with this expression where eta, the only condition that we have is that eta is not an eigenvalue of the matrix theta that defines the product. Okay? So in fact, all the subrimany structure that we have are somehow are isometric to this one with a fixed eta by rescaling. Okay, and this condition here is basically to assure the Brecht generating condition. Okay, if you ask for x1 or for eta and theta to be a basis of R2, it's basically because the bracket of x1 and x2 here has this expression. Okay. So, and then our problem, our optimal problem that we are interested to look at geodesics is basically this one. With this notation, we are looking for Lipschitz curves that satisfies this with contouring R2 with the condition that we are interested, bounded, essentially bounded, measurable. Okay, and that minimizes this distance. What is basically equivalent to minimize the energy function, okay, and that's where the Hamiltonian appears. And we can actually calculate the functions A, E explicitly. That's basically lets us to obtain the Hamiltonian in this case. Okay, the Hamiltonian is depends on the function A1 and A2. Okay, and here we have, by some quite simple calculations here, we can actually obtain what happens in the vertical part, meaning basically in the fiber that you have in your cotangent bundle, okay, and the horizontal part, okay. And the interesting part here, and that's why you see that there's basically one structure on Superman structure, that this doesn't depend on anything, just on the group, okay. Here, because theta, remember that theta basically says in which Salburli group you are, okay. So basically it only depends on the group that you are looking here, and that's the equation of a pendulum. And we recovered this result for Vernishi and Gershkovich, okay, from 1988, that he works with non-monotonic sphere in two-dimensional groups. It's another thing that he does is different from ours. But the point is that when we saw this and that, where the problem started is, if you look at the case where the trace of theta is 0 and the determinant is 1 here, that's precisely, not precisely up to a homogeneous space, up to a quotient here, of the case of S2, SA2, and SAD2. Okay? If you consider, basically, what I'm saying is that if you go to the homogeneous space here, when theta is 0, -1, 1, and 2, then this SC2 is basically d theta by a discrete subgroup, where d here is basically 2kp, 0, and k. Okay? So basically SC2 is recovered as this, and SA2 up to some isomorphism is basically g theta, where theta here is precisely 1 and -1. Is the group of the proper motions of the hyperbolic plane, if I'm not mistaken. Okay? So, and the point is that in both works, the works of, here is basically a survey that has all the works of Sechko and his students, his PG students. The point is that this kind of system here appears basically as a simple pendulum, and you can integrate it by elliptic functions. Once you integrate it by elliptic functions, basically the idea was in their work that they separate that they look at the dynamics of the pendulum. That's quite well known. You have a pendulum under some identification, and then the dynamic of the pendulum is basically like this. Sorry. So meaning that you have basically 3 regions, 1, 2, 3, 4 heteroclinic orbits that connect saddle points, 2 focus, and here, since we are identifying this as a cylinder, you have basically periodic orbits. So you have lots of periodic orbits, and here also, with exception of these heteroclinic curves that connect the saddle. Okay, and the idea was, in these works, basically you separate this in 5 regions. Okay, the region inside the heteroclinic orbits, the 2 equilibria inside also these heteroclinic orbits, the 3 saddle points that are true because of their identification, and the region outside. And the result that they got were that in each of these regions, of course, the equilibrium you can calculate explicitly, but in each of the regions, they were able to explicitly calculate the solutions and obtain all the information that you want. Okay. The problem is that this, I cannot affirm with 100% of certainty, but we cannot necessarily integrate by elliptical function. At least I couldn't do. I look up how can I prove that some equation cannot be integrated by elliptic function, but it's not so true. Okay, so we try to do a different approach, a more qualitative approach. Okay, so that was basically the idea. And you see that, of course, once you have the vertical dynamics here, remember that this And this here is just the exponential of the matrix that evaluated C. Okay? It's basically you are rotating the R2 components, depending on the matrix, of course. Once you have the dynamics of phi here, and then everything here is understandable. So everything lies on the vertical dynamic. Okay?
So there's feature in this case of SU2 that people have done, the equations are very much different from this.
I actually don't know. I know that in this work of Vershnicki, he obtains all the vertical equations for all the groups, basically by looking at the structural constants. But he doesn't have the analysis there. I know that there's the analysis because I found the paper, but it's quite dense. So since that's the starting point, we focus on the solver. But I believe it is. Of course, when the determinant is 0 and the trace is different to 0, we are basically in this case here, just to comment. Well, the case of S1 times the only solvable group of dimension 2. Okay, in this case, it's integral by elementary functions. Okay, so the only thing that they had in this survey in the 5 or 6 paper on the subject, because they were doing by steps, were a corollary that says that the cut time, that's what basically we are interested in, the time where you lose optimization coincides with the period of the solution of the problem. Okay? Meaning that here, since you are outside, of course here, period should be understood as infinite, because you don't have a period. But here outside, remember that you have a curve, so that's finite period, here also and here also. And with the exception of these 2 points here, these 2 equilibriums, okay, that you have some, you have a way to calculate also to where this period function converts. That's 2 pi over the root of minus the determinant of theta. You have actually that basically all the results here says that the cut time coincides with the period of theta. Okay, so the idea was to do basically that. Try somehow to look at the dynamics of the equation that we have here, that's much more complicated, and see if we can somehow recover that. Okay? And one thing that they use to estimate this period, to get an upper bound, is what we call a Maxwell point. A Maxwell point basically is if you have all the geodesics, since we are in the invariant case, start at the origin. So if you have a geodesic here, okay, and you have a second geodesic here, meaning solutions of this Hamiltonian, and they intersect at some point and are different in every point before, so this geodesic here is not optimal after this point. I think that's a classical result. And basically, system with symmetries, as is the case on Lie groups and homogeneous space, have a lot of symmetries. So the idea was to basically find this Maxwell set and the Maxwell point and try to analyze this kind of thing, okay, without solving the solutions. Okay. Okay. And what's the idea basically here in this context is to find symmetries of the vertical part, okay, induce this symmetry on the horizontal part by the exponential map. The exponential basically the solution in the direction of the covector here. This covector here is basically an element of the cylinder, remember? I didn't tell you, but basically we reduce our problem to a cylinder as 1 times r because we can, we just look at geodesics that are arc parameterized, arc length parameterized. Okay, so basically this is a map from a cylinder that's associated with the covectors, and at time t, you look at the solution there on the cotangent band of the Hamiltonian and project. That's the geodesic, the exponential. Okay, so you induce the symmetries here, and then basically we find covectors that are not fixed points for the symmetries on the cotangent bundle. However, their projection here at time t are fixed. So that's the basic idea, like in the whole paper, because they do that, but they do that basically by calculation and calculation, and the idea is basically that. You find symmetries, and you see that on the cotangent bundle, they are not fixed point, but when you project, you have fixed point of this symmetry. And of course, the symmetries have to commute with the exponential method. Okay? And here is the phase portrait of the vertical dynamics in the regular case. What's the regular case? The case where the determinant and the trace are different from zero. Okay? And you see that's quite nice in the case where the determinant is negative. Okay? It's almost the same one as the simple pendulum, but with some deformation. And the problems with this deformation is that you lose a lot of symmetry. In this case here, the pendulum, simple pendulum, have 8 symmetries. No, 7, 8 with the identity. And here you have just 4. Luckily we have just 4, and 4 was enough to get some result. Okay? And if you are in the determinant, negative here is worse, because the points here that were saddle points there becomes one repeller and one attractor. Okay? But it's still, you still have the same kind of behavior in the sense that you still have heteroclinic orbs connect saddle points. Okay? And here also, those are saddle points. And you can still divide the region in basically 3 regions. That's the regions inside and outside, and the boundary that are the heteroclinic points. Okay, and here also the same. Okay, region inside and outside. And we basically look at the periods of this guy. Here, all points that are not equilibria have, and not inside the heteroclinic orb here, you have finite period. If you are in the heteroclinic orb here, you just say that your period is infinite. Here also, you say that your period is infinite here inside. And here, it's nice because you have a nice property of convergence of the period, of course by looking at sections, that converge to 2 pi divided by the root of minus the determinant t. Okay? And you still have symmetries. For instance, here you can easily see that you have the symmetry related to the origin. Okay? You have another symmetry that's basically you get one point here, translate it by p, and go under by minus r, meaning that this curve here will be taking this curve here. And you have a third symmetry that's basically you get here, make a reflection, translate by pi, that will be here by the identification, and then you just go with r in negative time. So this part is symmetric to this part. So here you get here. And the second one now. Okay, so basically are this kind of symmetry that you have. Okay? And what do we do? The idea is the same. We get the symmetry, this discrete symmetry, induce it in the solutions of the vertical part. Okay, you get a solution from 0 to t, and then you induce the symmetry as basically looking at the solution given by this expression. Okay, so you induce the solutions, and basically what's doing here is what I commented here. So this solution here is taken into this solution here by the first symmetry. This solution here that goes through this one is taken by the E3 and so on. Okay, and this one that makes here and here by E2. Okay, and then you use, and that was the part that we actually didn't need the explicit solution. Okay, we have basic equation on R3 here. So that's a R2 solution, that's a R component, and we can integrate. We have the integral solution. Okay, we don't have a explicit solution, but we can integrate that. So we can again define the GI, basically the projection of the solution associated with the curve that I obtained here. So get Ci of this curve goes to this curve. Okay, so it's still a curve that's still a solution of the pendulum. So you project it. You define it as GI. That will still be a geodesic because geodesic are basically projection of the solution of the Hamiltonian. Okay, and you can explicitly calculate it using the integral form. And that was basically the most important part, because without the solution you can still obtain relationships between the solution after the action of Ci and the initial solution that you have. Okay? So, finally, what we do, remember that what we want is basically, we want to look at endpoints. So we are changing solutions by this kind of symmetry. So basically we have to look at the endpoint, when the endpoint coincides, and not the other ones. So basically what we have is that since we are in a context where length minimizers always exist, okay, you define this as the endpoint solution as get a t and a g and associated gi of t, okay, and that depends only on the point, the final point, not on the whole solution. And you can explicitly calculate this action as this expression here. Remember that you are in R times R2. Okay. Okay, so the same way the endpoint in the pre-image of the exponential basically takes C, an element of the cylinder, in a positive time, through lambda t, or lambda t through lambda I t, where lambda I here is the endpoint also of the solution on the vertical part, and you have this relationship here. Okay, so lambda 1 is minus lambda 2 is basically the final point of the solution associated with lambda initial, evaluated t plus pi, and so on. Okay, and by construction you have this conjugation. So the idea is quite simple. Okay, and with that we can actually calculate the Maxwell stratum and the Maxwell set that are basically the Maxwell points associated with these symmetries. Okay, how do we do that? No, we define as the Maxwell set I associated with the symmetry epsilon I. Okay, and their projection to the group as the Maxwell set, and of course by construction, if a point belongs to the Maxwell I, then this point is necessarily a Maxwell point because you start at the origin and you connect there by definition. Okay, that was the basic idea. And then how can I actually characterize this Maxwell set, and am I able to actually get some relationship with the period as I told you guys? And the answer is yes. So we almost didn't do any calculation, just qualitative study of this kind of thing. So fixed points behave like this. Okay, fixed points to the endpoint symmetry has this property. You have the symmetry 1, okay, so you are in the axis. If you have symmetry 2, you are actually at the origin. And if you have symmetry 3, basically you go back to the plane. Okay, so the Maxwell set basically lives on this plane union with the real line. And again, that's different from the simple pendulum because they had 8 sets to analyze. Okay. And basically that reduces our work to find the zeros of the component of the exponential. So that simplifies a lot the work. Okay, we don't need to estimate or do things like that. We just need to look at the zeros of the components. Meaning we are looking for solutions here that start at the origin. I don't have color. Let's start at the origin and do this kind of behavior. Okay, and solution that goes here and somehow touch the plane at some point. If we find this kind of solution, we have to analyze that. Okay, we start with the case where you go back to the z-axis. Okay, that's basically use natural trivialization and see that you never go back to the axis. Okay, it's not so hard. The idea is basically you trivialize your fiber bundle, and then you see that the solution on the second component has positive derivative with some condition, and then it never go back to the. There's some direction that has always positive derivative, meaning that it can never goes back to the axis. Okay, and they basically, so we are left to look at the Maxwell points that are associated with V3, meaning that the points where Z0, and remember that you cannot be a fixed point of the vertical part, meaning that you have this kind of thing. Okay, and that's basically analyze this function. That's quite easy because you just need to look at what happens here and what happens with the solution Z. So if you have a periodic solution, basically phi is a reparameterization of 0 to pi. Okay, so you have something like this. Okay, and let's say what we do. And if we are in the case where you don't have finite period, basically you have something that can go up and then stabilize in some -1. Okay, and what's Z? The component Z is basically the signed area of this kind of guy. You just sum areas. So basically, in this case here, the idea is basically you sum this guy with this guy here. Okay? So this will be, if you start here at a value t0 that we'll explain later, this will be a first zero. Okay? And the point is that the first zero is precisely the one where this condition here fails. Okay? So actually what you are looking is where is the second zero. And the second zero is precisely 2 pi. Well, 2 pi in this, like the period of the function phi. And in this case, what you have is if you started here and phi asymptotically approaches some of the, in this case -1, as t goes to infinity, you have basically that you have 1 0 here somewhere, and then after that you cannot change the sign of your component C. So you have just 1 0. Okay, so the problem of finding points of where the problem of finding Maxwell points basically lives in finding zeros of this function Z that condition it to this this restriction. Okay, so basically here what you do is you see that the solutions of phi, although not necessarily computable, have some nice properties. Here basically says that the cosine of this guy is an odd function. Okay, and then basically you analyze the sets of lambda. Here is the point of the cylinder. Here is the solution associated. So basically you are looking at the set of times where you pass by pi over 2 and pi over 2, minus pi over 2. You are looking at this set here, in this case. So if your solution are here, you pass maximum 1 time by this. If your solution are outside and is periodic, you can pass an infinite number of times. So basically, you look at the cardinality of the set. Okay? And in fact, there's a nice relationship between this set and the period, that the period is basically the infimum of this cardinality here. Okay? And you have this result. So basically the cardinality is 1 if Z has at least 1 0. That's this behavior of this function here. Associated with solutions that have infinite period. Okay, it can be, in the case where the determinant is positive, the ones that are inside the region. And if the cardinality is greater or equal to, you have actually an infinite numbers of 0, because you have a periodic function, and they are always 2 times one element of here, or a multiple of the period. And the infimum of the time satisfying both conditions is precisely the period. Okay, so actually what we get is this result, this really nice result that says that, that's the definition. What's the cut time that we are actually interested in? The supremum, where your G is optimal up to 0 in this interval. The first Maxwell time is the infimum of the time that you are in this set. Okay, and what we get is that for this symmetry we are still able to get actually some condition. We are able actually to characterize the whole Maxwell set associated with the symmetries. Okay, the first Maxwell time, the first time that you have a Maxwell point, and this one is basically most of the points are obtained here like this. For most lambda, actually just lambda different from the fibers over pi over 2 minus pi over 2. we have this because the maximum time you already lost your optimality. And the points that are actually on the fiber, we use that trick. That's a trick that are related with conjugated points. What's the idea is basically that you can, points that are on this fiber, you can approximate it by solutions, okay? By solutions here, where you still have that this solution have first the Maxwell time is finite, okay, and they converge here. So basically, what that's saying by the property that Maxwell point satisfies, that your exponential close to these points here, your exponential map, since the point here and the other point here will be Maxwell point, your exponential map cannot be injective. So in particular, that's a conjugated point, and conjugated points are also the first conjugated time is also where you already lost your optimality. Okay. So we are able to get that to classify the whole Maxwell set for the symmetries, and they are quite simple. And the cut time here is actually estimated has an upper bound given by this period function in the extended sense. Okay, so the natural question would be, does that coincides with the cut time coincides with the period? We still don't know, because as I said, it's a quite recent work. We finished it this year, and the most difficult part is how do I analyze the singularities of the exponential, because in this contact problem, what happens is that your cut time is basically the minimum of the conjugated time, the first conjugated time and the first Maxwell time. So if we get the conjugated times, we have actually a formula, and actually that's not a question that comes from nothing. It comes exactly for the case of SA2. And that's nice, because it's saying that the cut time, it has a lot of properties, invariant by symmetries, they are constant on the solutions. And interesting enough is the case of SA2 or the pendulum. You have that this invariance here is measured by what he calls the energy there, because we still have in the simple pendulum that the solutions also are basically curves of constant energy. Okay, but here we don't have it at all. So what we have that's equivalent is that the solutions here are, well, maybe the cut time will be invariant on the solutions of your vertical part. Okay, so the great problem is how do I analyze the singularities of the exponential just without calculating explicitly the exponential. Okay, we already have some symmetries for the exponential. There's a nice relationship using basically left invariance, but we still don't know how to calculate that explicitly. Okay, so that's basically it. Thank you for your attention.
Questions? Because I'm doing solved manifolds with Elena, I would like to know whether
You're the one doing solved manifolds. Okay.
I mean, not the one.
No, sorry. No, because Lino is talking about, I'm working on it.
Yeah, so I would like to know how difficult it is to transfer single Riemann geometry to quotient bilances, if this is clear.
Actually, I didn't try that, but actually I did that. Where? The problem here, at least in this, I mean, that's basically what's happening. It's not a lattice, but it's a discrete subgroup is what happens in G theta, for theta is equal 0 minus 1, 1, 0, to the SA2 and the n-folds associated with it. But basically, I don't think you have lots of lattices on this kind of at least three-dimensional groups, because all the discrete subgroups here, because you need to have a discrete subgroup, okay? and the only one that I know are the central ones, because it's quite rigid in this, like this simple connected case. So in the only example that I have how to pass this to some quotient of discrete subgroups is the one from G theta and SE2. So I would not say explicitly. But yes, something to think. Actually, something that's not done here is basically, I haven't seen any kind of Supermanian geometry of flag manifolds. I really, like, I know that there's some results, but there's a lot of things, invariant Supermanian geometry that I haven't seen in the literature, like some strong results on flag manifolds, real or complex ones. So just to leave it in there.
I mean, but maybe that there are some results about this, like a completeness for horizontal geodesics, like this dual foliation.
Yes, but here you see that's different. We are not looking at foliation. We are, because the point is the horizontal path that we are looking here, it gives you a whole topological ball. So you do not have like submanifolds. Your dynamics is not like how can I say? Presa? I forgot the word. It's not trapped in some manifolds or foliations. You have that your dynamic is in the whole space. And that's the difference because of the Brecht generating condition. So that's why I'm telling you. Like this Brecht generating distribution is not so well used. Usually you do this kind of in geometry, you divide the horizontal and vertical part, and here you cannot do that. You have horizontal, but the dynamics of the horizontal is the dynamic of the whole manifold. And that's the point. I don't know if I express myself clear.
Any other question or comment? So let's think, Adriano. Thank you. All right, so we are ready to start with the last talk in this conference for enduring. It's a great pleasure to introduce to you Ethan Cotterill from the Evgeny Campus. He's going to speak to us about enriched inflection and second kind formula for linear series on our vectors. Please, Ethan.
Yeah, so thank you very much for giving me the opportunity to speak at this wonderful event. I'm going to talk about joint work with a bunch of people whose names are on the slide. So I have a couple of aims for the talk. I want to explain all the words that go into the title. And sort of a subsidiary aim is that, and I hope that at least the first part of the talk is understandable to my community of algebra students, of which there are a couple in the audience. Okay, so let's get going. I first want to explain sort of my own motivation going into this project. So I work in algebraic geometry, and in enumerative algebraic geometry, kind of the most classical paradigm in which you often find yourself is one in which you want to count, in some sense, the number of points in a degeneracy locus for a map of vector bundles. So if we prescribe that we have a map of vector bundles over an algebraic variety, and we impose that the rank of this map be at most some number, then for example, if that expected number is finite, you can ask for what it is, and the traditional way that you would approach this problem, for example, might be using some kind of intersection theory, using cohomology classes. In intersection theory, we have a tool, namely Porteus's formula, that allows you to express the cohomology class of a rank locus for a map of bundles in terms of the Chern classes of the domain and the target bundles. One feature of this basic paradigm over the complex numbers is that the number of solutions, whatever it is, and provided you count it with sort of appropriate schematic multiplicities, is always is always uniquely determined by the numerical, by sort of the underlying numerical invariance. But you can then ask yourself what happens if instead of working over the complex numbers, you work over some arbitrary base field. And now, all of a sudden, the number of f-rational solutions to your enumerative problem, in general, won't be unique. So for example, if you ask the most classical, perhaps the most classical enumerative problem in algebraic geometry is counting the number of lines on a complex cubic surface in P3. And in that case, the number is 27 over the complex numbers. But if you ask to do the same count over the real numbers, the answer is going to depend on the topology of the real locus of your cubic surface. So that brings me to the numbers that are on this board. So for a real cubic surface, you can see 11, 15, or 27 lines. Okay, so I just want to contextualize this a little bit more. There are a variety of different contexts, slightly different paradigms within algebraic geometry where you can ask sort of very similar sorts of questions. So more than one person in this conference has talked about Gromov-Witten theory. So for example, you can try to count holomorphic maps to a target variety subject to certain incidence or contact conditions with respect to subvarieties. Maybe the most famous example is counting the number of rational curves in a quintic threefold. And if you try to do the analogous count, I wrote complex numbers again, I meant the real numbers here. The real analog of the complex counts from Gromov-Witten theory are what are known as Welshing G-invariants, which amount to Gromov-Witten invariants with signs. Today I'm going to be more focused in a slightly, well actually, I am going to be interested in a paradigm that generalizes this Welshing J paradigm. So one way of fixing this issue of number not being conserved over an arbitrary base field is to work within the context of what I'm going to call quadratically enriched algebraic geometry. So what's this going to mean? So counting with signs over the real numbers is going to be a special case of this quadratically enriched algebraic geometry. In general, what we can do is we can compute formulas that are valued in the Grothendieck-Witt group of symmetric bilinear forms over the base field. And I'll talk about this more in detail in a bit. But yeah, so the idea is to replace the notion of number by quadratic forms. And Welshing J is a special case of this. And then something I won't talk about today, but which is in sort of a similar spirit and explains this 6 minus 3 on the board, that's an example of an expectation that you can compute doing random algebraic geometry. So specifically, if you try to compute expectations for cardinalities of solution spaces that you expect to be zero-dimensional, say over the real numbers or over p-adic field, for example, well, you can do that. And so, for example, 6 times square root of 2 minus 3 is exactly the expectation for the number of real lines on a real cubic surface with respect to what's known as the Cosland distribution on homogeneous polynomials, which is sort of the distinguished Gaussian O4 invariant distribution. But I won't talk about random algebraic geometry anymore today, just to say that it's sort of a piece with these other approaches that are more germane to what I'm going to talk about now. Okay, so in order to motivate quadratically enriched algebraic geometry, I want to take a step back in time and actually talk about a motivation coming from differential topology. So, oops. So for example, one thing you could try to do, a very simple thing you can try to do, is count zeros of polynomials with signs. So for example, if you have a polynomial with real numbers in a single variable with only simple roots, well, you just count, every time you see a zero, you just count the sign of the derivative, either 1 or -1. And then the point is that if you sum these signs together, the signs of the derivatives of the zeros, then you end up with sort of the simplest instance of what's referred to as a topological degree, which in this case is going to be completely determined by the degree of the polynomial, namely whether it's even or odd, together with the leading coefficient. Why is this called a topological degree? Well, in a much more general setting, if you're given a, say, continuously differentiable map between compact-oriented manifolds of the same dimension, you can define the topological degree of that map to be the integer multiplier that's associated with the induced map on homology, right? Because both of those homology groups are just copies of Z. So the map on homology is just multiplication by some number. And the idea is that this topological degree is a signed count of pre-images. So if you, the idea is that you fix a point in the target, you want to count the number. That's what this map on homology gives you, and it's conserved as points in the target vary. At least, yeah, I think without any assumptions at all. So these topological degrees, which are sort of global artifacts of maps between compact-oriented manifolds, are sums of local topological degrees. By the local degrees, I just mean that numbers, so the signed numbers of pre-images associated with a fixed point in the target. And you can specify these local degrees. You can also specify these local degrees in a completely analogous way using homology, this time relative homology. And in fact, this is exactly how Milner formulated these things originally. But now the point is that there's an issue of how to calculate these topological degrees, and in particular the local ones, at points that are non-regular critical values. So if x is a regular value, which just means that the differential induced at the level of tangent spaces is an isomorphism, as a matrix, this linear map is just given by the Jacobian matrix of partial derivatives. And the local degree associated with a regular value is just the sign of that Jacobian, of the determinant of that Jacobian matrix, because the sign detects locally exactly whether your map F is locally orientation preserving or reversing. Okay, but then, so in the 1970s, Eisenbud-Levine and also Kimchiashvili on his own were interested in the problem of how to compute local degrees at not necessarily regular values. And what they found is that algebraic geometry gave a natural way of resolving this issue. And so it's sort of at this stage that I hope that the community of algebra students will maybe start to pay attention. But yeah, so to be concrete, let's assume we have a germ of a map. I'm having trouble using this. Yeah. so this is just a local instantiation of the map near the origin. We'll assume that the origin is sent to the origin. And let's assume that each of the component functions of our map is C infinity. But now, and this is what makes the connection with algebraic geometry robust, we're going to make the crucial assumption that our map is finitely determined, which means, so this is a technical condition, but it's very important, and it means just that there's some finite cutoff threshold for which the map and essentially can be identified with its order k Taylor expansion for all purposes of topology, for example. More precisely, that f and its order k Taylor expansion are contact equivalent. But I don't want to go into precisely what this means. So because of this finite determination condition, we can effectively identify the C infinity components of our map with their Taylor series expansions. And then in analogy, perfect analogy with what we do in algebraic geometry, I'm going to define the local algebra of this mapping germ near the origin as the quotient of, so a ring of power series in the variables of the ambient space modulo the ideal of the parametrizing function. And assuming assuming the zero, assuming that the zero of f in 0 is isolated, this local algebra attached to my mapping germ is a finite dimensional vector space over the real numbers. And in terms of algebraic geometry or commutative algebra, this means exactly that that the local algebra is an Artinian local ring, which I haven't talked about yet in the commutative algebra class, but we'll get to it soon. Okay, but there's a lot more that's true. So this local algebra has a lot of interesting structure. In particular, there's some orthographical errors here, but by the 60s, Berger had realized that, so important fact, that this local algebra is actually a Gorenstein ring, which is a special kind of Artinian ring. In particular, it has a one-dimensional socle that's spanned by the residue of the determinant of the Jacobian of the mapping germ. So we'll see sort of what this means in a concrete case in a second. I don't want to belabor the definitions yet, but we'll see what this means in an example. Moreover, and this is very important, the local algebra is endowed with a distinguished symmetric non-degenerate bilinear form, which today is what we would call the Schneider storage form. And what Eisenbud-Levine and Kim-Shishvili showed is that the topological degree is actually computed by the signature of this bilinear form. More specifically, slightly more generally, what they showed is the following. So if you have any real linear functional on the local algebra that's that its value on the socle is 1, then the signature of the bilinear form that we define in this way, from the functional, is exactly the topological degree of the mapping germ. Which in particular implies that Stejner-Storch computes the local topological degree. So let's see, maybe it's at this stage that I try doing an example. Almost. Okay, so let's consider an explicit example now. So in this case, I'm identifying R2 with C, and I have this holomorphic map, which is just a ramified cover of the disk. So the point is that if I think of z in terms of its real coordinates, then so f of z is z squared. What does this mean in terms of x and y? Well, f of x comma y, if you expand things out, is x squared minus y squared and 2xy. And the Jacobian matrix associated with this map is, well, the Jacobian determinant is just, you take the partial derivatives with respect to x and y, so you get 2x minus 2y, 2y, and 2x. You get 4 times x squared plus y squared. This is actually an artifact of the fact that, more generally, of the fact that this is coming from a holomorphic map. But the point is that you can see immediately from this example concretely that the Jacobian determinant is strictly positive away from the origin. So in particular, at every regular value, you have you have 2 preimages because every non-zero complex number has 2 square roots, and the map is orientation preserving in each of those preimages by the positivity of the Jacobian. And now what I want to do is, so in particular this means that the topological degree of the germ is 2. Okay, but now I want to do the same thing. I want to work out the topological degree, but on the basis of the EKL theorem. And if we apply the theorem, what that means is applying the multiplicative structure of the local algebra. So how is that going to go? Well, it's easy to work out in this case that the local algebra is 4-dimensional with the real numbers. The multiplication is quite simple. Yeah, right. So there's a basis. We can fix a real basis, just given by the residues of 1, xy, and x squared plus y squared. And then multiplication in this basis is easy. And in particular, what we see, so I mean, one thing that you see right away is that at the topmost degree, this x squared plus y squared up to a multiplier is just the Jacobian again. So now, how do we define the real functional that's going to induce the bilinear form that allows us to compute the topological degree? Well, you just set its values on a bunch of the base elements to be 0, and then you're only required to map the Jacobian to 1, which fixes the value on x squared, on the residue of x squared plus y squared. So you can codify all of this in a table, which gives you a matrix representation so you can then use this to define, according to our recipe, a bilinear form, which is given by this table, and which diagonalizes to this matrix, which has 3 positive entries and 1 minus. So you just sum the signs along the diagonal, and you get 2 as required. Okay, explain how you might find the César-Storch form if you were looking for it in the wild. And this is where the connection with commutative algebra becomes even more interesting, I think. So we're going to assume the following setup. We were just talking about this very recently in the commutative algebra class. We have an extension of rings, polynomial rings with the same number of variables. And so, an extension of rings that makes, I think the statement is supposed to be that B becomes a finite A module. And so this extension of rings is the algebraic version of a finite map that's induced at the level of spectra. The fact that this map is defined by, this extension is defined by polynomials is reasonable because of our assumption that we only have finitely determined mapping germs. And then I'm going to make an additional assumption, which is sort of more restrictive, but pedagogically very useful. So I'm going to further assume that in the complexification of my map, the only preimage of 0 is 0. The utility of this assumption is that So the Nostellensatz then would say that the radical of the ideal cut out by these parameterizing functions is just is exactly the maximal ideal in 0, which means then that the ideal determined by these parameterizing functions is contained in a unique maximal ideal, so that I can then identify sort of the global coordinate ring of coming from this map given by quotienting my ring A by the parameterizing functions with the local algebra that I would get by passing to the completion. And so what's interesting here is that in the setup, there's actually a flat family of sort of fiber algebras that's parameterized by R to the n, and then it's over, so here y is a point of R to the n, and then over the center point we recover sort of the local algebra attached to the origin. Now the idea is that whenever the point y is a regular value, the associated local algebra is just going to decompose as a product of a certain number of copies of R corresponding to the real valued points in the fiber, together with an Artinian ring whose spectrum is just a union of complex conjugate pairs that you see in the fiber when you complexify. So the topological degree at that regular value is just the sum of the signs of the Jacobian determinants in the R value points of the fiber. And now the game is that we need to find a continuously varying family of bilinear forms on these fiber algebras whose signatures at regular values are sums of signs of Jacobian determinants, and then continuity is going to ensure that the signature is locally constant. So in particular, sort of the limiting bilinear form is going to compute over 0 is going to compute the topological degree, and we'll conclude. And how do you do that? Well, there's a canonical way to, like pun intended, to solve this problem. Namely, if you consider, again, we have this. Oh, that was unintentional. Again, if you have, we start with this extension of rings. Thanks. We start with this extension of rings A and B. Oops. The idea is that if you consider the canonical module associated to this extension, or the dualizing module in sort of more of an algebraic geometry terminology, well, that is the B module given by A module homomorphisms from B to A. And by construction, B as an A algebra has this presentation as a quotient. So because of our finiteness assumptions, this algebra B is actually just a global complete intersection over A, so in particular it's Gorenstein, which means that the dualizing module, which again is the module instantiation of the sheaf of Kähler, so the relative sheaf of Kähler differentials, or the dualizing sheaf, is a free B module of rank 1, and this is what was worked out in the 60s. It has a canonical generator, namely the following A linear functional, which I'm denoting by T, and this functional has this amazing form. You send a polynomial in the xi's to the trace of the quotient of the polynomial by the Jacobian determinant. And here, so by trace I mean the field trace that's associated with, if you take, so the field of trace associated with the extension of, the field extension induced at the level of function fields. So in other words, if you have if you have an element in the larger function field and you consider multiplication by that element as an endomorphism of the base function field, then trace refers to the trace of that map. What's nice about this is that T restricts to R linear functionals on every fiber algebra parameterized by R to the n. And so the idea then, to conclude, sort of all we have to do is assemble our bilinear forms using just very slight renormalizations of the form that we saw in the example. So this is a little bit of a sketchy proof, but I hope it gives at least the flavor for how this works. Okay, so what's interesting and is part now of more recent history is that about 10 years ago, Jesse Cass and Kirsten Wickelgren realized that the EKL topological local degree over the real numbers could be vastly generalized to compute what are known as motivic local degrees in the sense of Morel and Vygotsky. So again, this is as I said sort of in the introduction, now what's going to happen is that instead of considering signs, we're going to consider elements of the Grothendieck-Witt group of quadratic forms over an arbitrary base field that doesn't have characteristic 2. Actually, I said quadratic forms here, but because of this assumption on the characteristic of F, I can treat quadratic forms and symmetric bilinear forms as essentially the same thing. So what is this Grothendieck-Witt group? Well, it's the group completion of the semi-ring with operations direct sum and tensor product, so that you get on non-degenerate symmetric bilinear forms. And what's interesting about this Grothendieck-Witt group is that it's completely computable. So it's known that it's generated by these atomic classes that I've denoted by A that are associated to non-zero elements of the base field, according to this recipe. And it has explicit relations, too, that define it. In the story, the hyperbolic class, which is the sum of these two atomic classes 1 and -1, is distinguished and in particular is going to show up in some formulas that I'll show in a minute. So what are examples of Grothendieck-Witt groups that you should keep in mind? The very first example is the Grothendieck-Witt group of the complex numbers. The point being that, so over the complex numbers, the only non-trivial invariant of a quadratic form is its rank. So correspondingly, the Grothendieck-Witt group is isomorphic to Z. And then, if you consider other fields, so for example, the Grothendieck-Witt group of the real numbers is isomorphic to Z cross Z, where the two factors correspond respectively to the rank and the signature of the quadratic form. Whereas if you take a finite field, now the Grothendieck-Witt group turns out to be isomorphic to Z times Z mod 2Z, where these two factors correspond. The first factor, again, always corresponds to the rank of the form, and the second is the discriminant up to squares. So one point that's probably obvious from what I've just said, but that I want to emphasize here is that for every field F, we have a forgetful map. from Grothendieck-Witt group of F to Grothendieck-Witt group of C given by the rank of the quadratic form. So it's in this sense that we think of formulas that are valued in the Grothendieck-Witt group of F as quadratically enriched versions of classical formulas that are valued in the Grothendieck-Witt group of the complex number. Okay, so yeah, so now in the remaining time, yeah, so I want to explain a little bit about how to compute quadratically enriched formulas, and in particular quadratically enriched classes of rank loci. So, so if we have a rank locus attached to a map of vector bundles on a smooth variety X, then there are sort of two technical conditions that, two basic conditions that need to be satisfied. This isn't completely ironclad, but two conditions that generally should be satisfied in order for this technology to work well. The first is that the rank locus should be realizable as an Euler class, which means that it can be interpreted as a top Turing class of a vector bundle on X of rank equal to the dimension of X. The second condition is an orientability condition, actually relative orientability, which means that the Hom bundle from the determinant of the tangent bundle to the determinant of this bundle E should be a tensor square. And actually, in order to be able to compute local Euler indices explicitly, this isomorphism needs to be realizing this Hom as a tensor square needs to be explicit. I want to mention that this first condition, again, is not absolute, because it's very easy to construct examples of rank loci that are not Euler classes. But there's sort of a standard way to promote your favorite rank locus that isn't necessarily an Euler class to an Euler class at the price of having to pass to a Grossman bundle. So perhaps at the end, if there's time, I'll say a little bit more about this, but in a specific case. But that's to say that in the best possible situation, this first condition would be satisfied, but if it isn't, there's a way to sort of fix that. Anyway, a fundamental result due to Katz and Wickelgren says that when these two conditions are satisfied, there's always a global quadratically enriched formula for the Euler class that's valued in the Grothendieck-Witt group of F. And that global class is a sum of local quadratically enriched degrees that you can compute using the zero of any non-zero global section of your bundle. And very famously, they applied their machinery to show that the global A1 Euler class of lines on a smooth cubic surface is 15 times the atomic 1 class plus 12 times the atomic minus 1 class. And you should notice in this formula, this already recovers the classical formula because we have the classical formula of 27 lines on a complex cubic. The rank map just says that you sort of forget the signs in these atomic classes and you just sum the 15 with the 12.
And the difference is always 3, right? I mean, when you change this other classes.
Yeah, I mean, I think the fact that if you take the difference, I mean, I think that 3 is the same 3 that we saw before, but I sort of forget how to really explain that. But yeah, it's not a coincidence. Okay, so yeah, I'm short on time as ever, but okay, so how do my own work fit into this setting? Generally speaking, I'm interested in the behavior of linear series on curves and what this implies about the moduli space of curves. So, so the idea is that the way that you specify a holomorphic map from a curve to a projective space algebraically is is via what's known as a linear series. So it's just a pair of a line bundle together with, so a line bundle of some degree d together with an r+1 dimensional subspace of holomorphic sections. The point being that the space of sections gives you, well, when you projectivize, you recover this p to the r, and you sort of think of these sections as coordinates on the target space. And the fundamental local invariant of a linear series is its inflection in a point, as measured by derivatives. So what is this? I mean, it just means that if you fix a point on the curve, you're interested in to what extent the vanishing orders of your holomorphic sections deviate from the generic sequence of numbers from 0 to r. So that's a local version of inflection, which just measures some kind of twisting in space. And actually, sort of very concretely, how do you visualize this? I mean, the prototypical example for local inflection is what you see in calculus class. So you have an inflection curve. You have an in the origin, right? I mean, so this is y is equal to x cubed. You have the second derivative vanishing. I didn't draw this very well, but you get the idea, I think. And the idea is that parametrically this is just t goes to t and t cubed, and the idea is that the jump in this exponents reflects this deviation from the generic sequence of vanishing orders that I was talking about. So you can then sum over points, and you get a cumulative or total measure of inflection of your linear series. And there's this famous formula due to Plücker from the late 1800s that determines the total inflection of a linear series on a curve, smooth curve of genus G, as a polynomial in G, the rank, and the degree, which is this formula that I put at the bottom. And so again, this is kind of just a very classical. This is just a very classical example of a formula that's completely deterministic in the numerical invariance of your numerator problem. But now what we can ask is if there are analogs of inflection over other base fields. I think I'll skip this. It's easy to realize inflection as an Euler class of a jet bundle, so a bundle whose fibers, it's a bundle over C of rank r+1 whose fibers are just sort of truncated Taylor series of sections up to order r in the point. So in particular, we can sort of check off this first technical condition that we were trying to satisfy in order to have well-defined Grothendieck-Witt Euler class. But actually, we then specialize a little bit more in order to satisfy this second technical condition, which is relates to orientability. So we specialize to linear series on hyperelliptic curves. So what is hyperelliptic curve? Well, it's just a 2-to-1 cover of P1. So a hyperelliptic curve means that something like this, say, this is my point, this is my point infinity at P1. I have a 2-to-1 cover. I have a 2-to-1 cover just given by, so if the level of a local equation, my model is y squared is equal to f of x. I have this projection that just sends x comma y to x. And then in the picture, this projection is ramified over infinity. So we proved some A1 formula, A1 analog of Plücker formula in the setting. Point is that the global Euler inflection class is just given by a multiple of the hyperbolic class in this instance. And actually, what's more interesting is the local indices that sort of constitute this global class. So we also did some explicit calculations of local A1 inflection area indices. There's some numerology going on here that I don't really want to explain, but there are also these field traces that show up. So actually what this means, these traces refer to a trace map at the level of growth unique bit groups that's induced by post-composition from a field trace, in the sense of what we talked about earlier. And this is to say that, well, these are local inflection area indices in ramification points of a hyperelliptic projection. It's harder to compute these local indices away from the ramification points of the projection, of the hyperelliptic projection. How much more time do I have? 2 minutes? Started 5 minutes. 8 minutes? I mean, I'm not going to say a lot more, but okay. But I want to end by saying that there are other geometric and arithmetic paradigms that you could think about and try to apply the A1 package to. The main paradigm that is the focus of work in progress for us right now is where instead of looking at inflection points of linear series, we look at secant planes. What do I mean by a secant plane? Well, I want to think of this as sort of a global analog of an inflection point. So a secant line is just, so a secant plane is just some incident, some linear subspace of projective space of fixed dimension that has a prescribed incidence degree with my curve. So for example, a secant line would be something like this. This would be a tri-secant line with a curve. But in general, we're going to be interested in situations where the linear subspace has arbitrary dimension. And the idea is that if you do a little bit of work, you can realize, so the first point is that secant plane loci can be thought of as rank loci for bundles over over for example, a Cartesian product of the curve. If I have, I think this is a little bit hard to read, but the idea is that, I'll spell it out here. To realize, so if I ask for secant planes, d secant planes of projective dimension d minus r minus 1, what that means at the level of rank loci is that I have evaluation maps of sections that define my linear series to, I evaluate these sections in d tuples of points. I can do this in families, so there's a bundle version for this. L square brackets d is a rank d bundle whose fibers are sections, are evaluation, essentially evaluation sections in d tuples of points. And then I just impose that this evaluation map be of rank at most d minus r. And then there's a way to promote this description to an Euler class associated with a bundle over the product of, over a Grassmann bundle over I think this should actually be y to the d. So it's actually, yeah, there's a typo here, but there should be this would be a Grassmann bundle over the d-fold Cartesian product of y with itself. The point is that I can, I can realize secant planes as zero loci of sections of this tensor product of the dual of the tautological subbundle on this Grassmann bundle together with a pullback of this L to the D secant bundle. Yeah, so now the situation is more complicated than in the case of inflection points. This slide is just saying something about the numerology of these things at the level of generating functions. Yeah, hard to write down explicit formulas for the numbers of these things. But then I do want to mention that they have, so much like these jet bundles, again, we think of secant planes as being global analogs of inflection points. So at the level of bundles, the secant bundles are sort of analogous to the jet bundles in the sense that they have a natural inductive structure. And then, yeah, so then we have to do some Euler class calculation. What can I say? So I think the thing I'll end with is that the main way in which things are more complicated, in which life is more complicated when you try to compute A1 secant plane formulas as opposed to A1 inflection formulas, is that it's much harder to ensure that this relative orientability condition is satisfied. So we have to make it more flexible somehow, and we do that by a global Euler class in this setting to be a sum of local classes, and then yeah, we have some results about the structure of these classes depending on symmetries with respect to the symmetric group and also with respect to the hyperelliptic involution. So in particular, with some numerological assumptions, we can ensure that in certain circumstances these these generalized A1 Euler classes that are now defined with respect to choices of these divisors D are again multiples of the hyperbolic class. Yeah, so the very last thing I'll say is that if you want to learn more about anything that I discussed today, the very first thing I would do is take a look at this expository article of Eisenbud from the late 70s, where he explains the topological degree and the Schege-Storch form, which is sort of the key for all of these further developments. So, yeah, thank you for your patience.
Questions?
Can you somehow quadratically enrich the counts of just the connected components of some trilogy varieties, for example?
I mean, so I don't know what to say. There's I mean, not using the approach that I was describing, but I think if you use this, maybe if you use this approach based on, I don't know if you've seen this, the A1 Brouwer degree, maybe with that approach. Yeah, maybe in that version, maybe in that version you can do it. I'm not, yeah, I wouldn't bet my house on it.
Could you go back to the slide where you classify the things on the hyperelliptic curves?
Okay.
Please.
Okay.
So, for elliptic curves, and there is also some invariants in module 4 that give good reductions module P. Do you know if that could be used for studying elliptic curves on finite fields?
I mean, so actually, I think in general, there are people who are trying to use. So it is reasonable to expect that they're sort of non-traditional, they're non-trivial conditions coming from these A1 formulas that impose restrictions on sort of numbers of F rational points. So if you try to, do a sort of a more traditional classification of the possible number of F rational points, F rational solutions to a given enumerative problem, then you can hope that maybe that these A1, these Grothendieck-Witt valued formulas give you some non-trivial conditions on those possibilities. But I think in general that's hard. I mean, there certainly is something packaged in there, but extracting it, I don't know. I wouldn't know what to say. I don't know if people have actually done that in a successful way, in a very successful way over finite fields. I think over R maybe there are some interesting results. Thanks.
Other questions or comments?
I have a question. So we usually work with value semigroups when working over a curve or over a perfect field or characteristic zero. Is there a way to also quadratically enrich things to
semigroups?
To do value semigroups at points?
Maybe. I mean, maybe. I mean, what I would say is that the closest thing I think to that, maybe. So I guess one thing is I don't know how interesting that would be. Maybe that's interesting. I'm not sure what to say, but I think the closest existing thing to what you're asking about is they're sort of quadratically enriched tropical curves. So that somehow, at least philosophically, is close to what you're asking for.
Any other questions? So let's think even.
Just say a couple of words.
Is
it final closing? No, it's a very quickly. I just would like to say thank you to all the speakers, to all the audience, to all the participants, to all people that show the posters, and we hope to see you soon here in the IMEC. And for those people that we are traveling to Rio tonight, we are leaving here from the IMEC 6:30. Okay, but I suggest to meet in the hall 6:20. Okay, we are splitting three cars. Okay, and we need to make some arrangement between because of the luggage. We need to deal to see how to accommodate all the luggages in the three cars and the 10 people. I guess enough space.
Okay, so let's thank the organizers.